Hi dear students, welcome to today's online class. Today we go more into the details of UV visible or electronic spectroscopy. In the previous class, we had a recap of some important concepts regarding UV visible spectroscopy. Today, first of all, we discuss about most significant transitions in UV visible spectroscopy. We have seen that there are 6 different types of electronic transitions possible in a molecule, out of which 2 are most significant. They are, one is pi to pi star transition, and then n to pi star transition. Let us distinguish these 2 transitions. Like, what about the energy gap between these 2? Energy gap is more for pi to pi star, so larger energy gap, whereas n pi star require lesser amount of energy, it is lesser. When energy gap is more, then lambda max, the wavelength of the radiation used for the transition, will be smaller, right? So lambda max will be smaller for pi to pi star transition, whereas for n to pi star it will be larger, right? And also we have seen that this is a symmetry allowed transition which will be more intense. So intensity will be more, which we represent using epsilon max, that is molar extinction coefficient. Pi star, from pi orbital to pi orbital, same symmetry, so it is called symmetry allowed transition. Symmetry allowed, right? And because of that, this spectrum, the peak will be very intense, of the order of 10,000, and the intensity of n to pi star, which being forbidden, it is symmetry forbidden, the Emax value is quite small, of the order of hundreds. So these are the main difference between these 2 transitions. In the subsequent discussion, we will be referring to these 2 transitions in various compounds. Right. Now, we will discuss about the effect of conjugation on lambda max. Let us see. Let's say 2 molecules. One is ethylene, CH2 double bond CH2, and the other is CH2 double bond CH, single bond CH, double bond CH2. What is this molecule? This is butadiene, which is a conjugated diene. This contains only 1 pi bond. Here there are 2 pi bonds which are conjugated. Now, if you look at the energy levels, the pi molecular orbitals of these molecules, according to MOT, when there is a pi bond, there will be 2 MOs, one bonding and one anti-bonding, which is formed by the 2 p orbitals of the 2 carbon. This is pi 1 and this is pi 2. This is bonding orbital, this is anti-bonding molecular orbital, and we put an asterisk for anti-bonding. Now, the 2 pi electrons will be definitely in this orbital. During transition, what happens is that electron moves from pi 1 to pi 2, okay? We call this as HOMO, HOMO, highest occupied molecular orbital. And this is called LUMO, LUMO, lowest unoccupied molecular orbital. See, if a molecule contains a large number of molecular orbitals, transition takes place from HOMO to LUMO, which will have minimum energy, and that is most probable transition. Now, what about butadiene? There are 4 p orbitals and it will form 4 molecular orbitals. We can show the 4 molecular orbitals like this. Okay, and this is pi 1, pi 2, pi 3 and pi 4. Out of these 4 molecular orbitals, 2 will be bonding and 2 will be anti-bonding. These 2 are bonding, these 2 are anti-bonding. We put asterisk over here. Now the electrons will be filled in pi 1, there will be 2 electrons, and pi 2 there will be 2 electrons. Now, what about the transition here? It's possible between from pi 2 to pi 3, because this is HOMO here and this is the LUMO. Okay. Now what happened to the energy gap? When conjugation increases, when there is an additional double bond, pi bond coming in conjugation, what happens? HOMO-LUMO gap decreases. Here it is larger, here it is smaller. When energy gap decreases, you know what happens to wavelength? Wavelength increases. That means due to increase in conjugation, lambda max value increases, or it is called bathochromic shift or red shift. So note this point. When conjugation increases, there will be bathochromic shift or lambda max increases. Okay. Now let us go to the third point of discussion, that is, we have to consider the electronic spectra of some selected molecules. We have such 4 molecules in our syllabus. Let us discuss one by one. So we will get familiar with how electronic spectra looks like and how can we interpret the spectra. We start with the first molecule, that is acetone. Okay, acetone. Always we will draw the structure first. CH3, CO, CH3. Since there is oxygen, there will be 2 lone pairs. That means there is n electrons, non-bonding electrons are there. So what about the spectrum of this molecule? And what about the lambda max and epsilon max value? Let us see. The spectrum of acetone looks like this. There are mainly 2 peaks seen, right, like this. Can you predict these 2 peaks are due to which transition? I have told you already that the significant transitions are pi to pi star and n to pi star, even though there are other transitions like n to sigma star, sigma to sigma star, everything is there, but we consider these 2 mainly. So this is lambda max, this is lambda plotted against epsilon, intensity and wavelength. So this is the lambda max of which transition? See, intensity is high, lambda max is lower, so this corresponds to pi to pi star transition, right? The value of this transition ranges from 180 to 190 nanometer. It comes somewhere in this range. Exact value depends upon the type of solvent used. Remember, factors affecting lambda max, one is conjugation, another is nature of solvent used, right? Solvent polarity will affect the lambda max value slightly. And this peak is due to which transition having higher lambda max value, that is for N2 pi star, and this value ranges between 270 to 290 nanometer, and that is because of N2 pi star transition. So this peak accounts for N2 pi star transition, and this peak accounts for pi to pi star. This is very intense. Okay, intensity is high and this is less, lower, small. So that's about acetone. Okay. Now let us go to the next molecule. That is methyl vinyl ketone. We consider methyl vinyl ketone. Let's see the spectrum of this methyl vinyl ketone. Let us draw the structure first, and let us compare between acetone and methyl vinyl ketone. Methyl vinyl ketone, this is a common name. It is nothing but CH3 CO, then CH double bond CH2. It's a common name. Methyl vinyl ketone. What's the IUPAC's name of this compound? It will be 4 carbons, so but 3N2-on. Okay. Now, what is the difference between acetone and this compound? It has an conjugation, additional pi bond in conjugation. So naturally, what will happen? Pi to pi star and N to pi star band will move to larger lambda max. Remember that whenever there is bathochromic shift or red shift, it will be accompanied by hyperchromic shift also. That's a point to be noted. When lambda max increases, automatically E max also will increase. Similarly, if lambda max decreases, that is called hypsochromic shift or blue shift. That will be accompanied with hypochromic shift, that means decreasing E max also. Now this molecule also has oxygen, so there is heteroatom, lone pair is there, so N electrons are there. So this will also show mainly pi to pi star and N to pi star transitions. Let's see, let's draw the spectrum. It looks somewhat same like acetone, but the values are different. Okay, for this correspond to the pi to pi star band due to pi to pi star transition. Its value is 217 nanometer, whereas in acetone it was only 180-190 nanometer, and this is lambda max is 324 nanometer, that due to N to pi star. You can see wavelength is more for N to pi star, but intensity is less because it is forbidden transition. So in acetone, compared to acetone, pi to pi star transition has increased roughly by 30 nanometer. This one also increased by 30 nanometer. So what does it mean? When conjugation increases, when a pi bond comes in conjugation, then delocalization increases. That means the resonance effect increases. Due to that, HOMO-LUMO gap decreases. So there is bathochromic shift for both pi to pi star and N to pi star transition. Okay. Now we consider the third one. That is very comparable to this molecule. It is, the third one is buta-1,3-diene. The buta 1,3-diene. The structure is CH2 double bond CH, CH double bond CH2. Very much like methyl vinyl ketone, except that this doesn't have oxygen. So what? there is no lone pair, there is no n electron. So this molecule will have only which transition? Only to pi star. The major transition, only pi to pi star. So let's see how this spectrum looks like, that of this butadiene. It is like this. It is, you get only one major peak like this. That is only peak given by butadiene, and its lambda max value is roughly the same as methyl vinyl ketone. It is also exactly same, 217 nanometer. Then that is due to pi to pi star transition. A very intense peak, only one peak. There is no n to pi star transition. Why? Because there is no lone pair, there is no heteroatom. Okay, so it's very similar to the previous one. Now finally we have one more molecule, that is benzene. Okay, benzene is an aromatic compound. Aromatic compounds are characterized by very special kind of electronic spectra. Benzene, you know, benzene has the structure with cyclic conjugation. You know, there are 3 pi bonds and it is having a cyclic delocalization, cyclic conjugation. Okay, it shows a special kind of electronic spectra. It has got 2 types of bands. One is called primary band. Okay, it is showing 3 different peaks. Primary bands, there are 2. One is called E1 band, the other is E2. These 2 are together called primary bands. E stands for ethylenic. Since there is double bond, it is ethylenic bond, and E1 band is having a value of it is at 184 nanometer. Okay, and it's very intense actually. E2 is at 200 nanometer. Okay, in addition to primary band, there is a secondary band. Secondary band of benzene is represented as, is named as, labeled as B band, and it is having a value of 255 nanometer. We show only that secondary band, which is very characteristic of all aromatic compounds. It is something like this. See, this kind of finger-like fine structure is shown by all aromatic rings. Fine structure. See, the benzenoid, B stands for benzenoid. So the secondary band, benzenoid band at 255. So the lambda max of this is 255. Okay, 255. Remember, all these bands are due to pi to pi star only, because there is only pi bonds here, there is no n electrons. So pi to pi star transitions, but it gives different types of bands or peaks. It is because of the inter-electronic repulsion and the symmetry considerations make the electronic levels of benzene quite complicated. It is not simple. Actually, according to MOT, when we draw the energy levels of benzene, it is like this. You have MO configuration of benzene normally like this: pi 1, pi 2, pi 3, pi 4, pi 5 and pi 6. When we fill the 6 pi electrons, it is filled like this. Okay, so the transition can be from this, between these two. So we expect only one band for benzene, but it is not so. Benzene and all aromatic compounds give a large number of peaks, out of which the peak at 255 nanometer, which is called secondary band or benzenoid band, is having a very special shape, a fine structure. It is accounted for vibrational interaction with the electronic transition. So this is the vibrational interaction is giving this kind of fine structure for the secondary band in benzene. Okay, that is a very speciality of benzene and aromatic compounds. So that's about the electronic spectra of some selected molecules in our syllabus. Finally, we will just mention about some important applications of electronic or UV visible spectroscopy. We can note some important ones. One, we can distinguish isolated and conjugated dienes by UV visible spectroscopy. This spectroscopy is most suitable for distinguishing isolated and conjugated dienes. So to distinguish isolated and conjugated dienes. Let us take an example. Look at this. I am taking two molecules. Okay. What is this? This is an isolated diene. 1, 2, 3, 4, 5. It is penta 1, 4 diene. And let me take another molecule, this one, 1, 3 penta diene. These two can be easily distinguished by UV visible spectroscopy because this being conjugated will have higher lambda max, correct? Lambda max will be higher for this and smaller for this because here there is no conjugation, there is no interaction. So this will give a spectra something like that of an ethylene only. Okay? So that is one application. Now second one is we can distinguish cis trans isomers or geometrical isomers easily by this technique. Geometrical isomers can be easily detected, easily distinguished by this. Let's take for example, that is, if you consider the cis trans isomers of stilbene, okay, stilbene, you know, like this, stilbene. Which isomer is this? This is stilbene. Which isomer it is? This is on opposite side, the two benzene ring. This is a trans stilbene. Trans stilbene. Okay. Two benzene rings are on the same side. How you will distinguish these two? By UV visible spectroscopy. Yes? How can you distinguish these two? Anybody? Can you answer this? See here in the trans, the two benzene rings are on opposite side. Here it is on the same side. So what? When they are on the same side, what will be there? There will be steric repulsion. Due to steric hindrance, the two benzene ring will be kept out of plane. To get rid of this steric crowding, the two rings will be remain out of plane. When it is out of plane, conjugation. See, there is extent of conjugation here. You can see there is conjugation possible from one ring to the other, and that conjugation will be very difficult here in cis. So delocalization is very effective here. So this will have higher lambda max for this trans isomer, and it will be less for cis isomer. Not only lambda max, Emax also will be more for trans isomer. Okay, and here it will be less. If we can easily distinguish molecules by this. Now, apart from this, two other applications are, one is we can identify various compounds like polyaromatic compounds from, for example, if you consider monoaromatic like benzene with one ring, and naphthalene having two fused ring system, anthracene having three, etc. You can easily distinguish by UV visible spectroscopy again by the same principle. See, in our daily experience, benzene is a colorless liquid. Naphthalene, is a mothball, cockroach repellent. It's a white powder like compound. Anthracene having three ring is slightly yellow in color. Why this difference? These two are colorless. This is slight yellow in color. What happens when benzene ring is increasing in number? Extent of conjugation increases. When conjugation increases, lambda max also increases. So wavelength goes from UV range to visible range, and we see this as colored. When number of benzene increases, when conjugation increases, lambda max increases and it may eventually reach the visible range. And finally, the last application we mentioned here is that there is an important quantitative technique used for based on electronic spectroscopy, what is called spectrophotometry. Spectrophotometry is a quantitative analysis. We can estimate the solution of naphthalene in alcohol. Alcoholic solution of naphthalene we can estimate. Just like we do titration for estimation, quantitative estimation, we can carry out a spectrophotometry, or also called colorimetry. A very easy technique, colorimetry, which is based on Beer-Lambert's law, which A is equal to epsilon Cn. From this equation we can write A is proportional to C. So we can determine an unknown composition, concentration of a solution by noting the absorbance. The details of this technique you might have learned in the fifth sum portion. So these are some applications of UV visible spectroscopy. Now, in the last part of this UV visible spectroscopy, we have to be familiar with calculation of lambda max of dienes and conjugated dienes and alpha beta unsaturated ketones by certain rules, empirical rules called Woodward-Fisher rule in the next class. Thank you.